So let's start with this first question. If I ask you to determine the limit of a sequence, what am I really asking you to do?
Not add.
Not add, first of all, right? If the word sequence is what the question is asking about, it's not the same thing as series, which in particular means that all of those convergence tests and integrals and all of that other stuff that goes on in the tests that you apply to infinite series, those things don't apply here because we're not adding anything. We're just taking these numbers, if you like. So if n is equal to 1, we get 1 over the square root of 5. If n is equal to 2, we get 2 over the square root of 9. If n is equal to 3, we get 3 over the square root of 13, etc., etc. So we're just taking those numbers, and I want to know what those numbers are tending towards as n tends toward infinity, if anything. So how do you find the limit of a sequence? What's the only tool we have here to find the limit of a sequence? Derivatives, but what derivatives of what? Where am I going to apply derivatives?
L'Hopital's rule.
Yeah, L'Hopital's rule, exactly. So I have a limit here, which if we think of it as a limit of a continuous function, replacing n's by x's, then this limit is indeterminate, because both the numerator, as x tends to infinity, and the denominator, as x tends to infinity, are tending to infinity. So this is a limit having the indeterminate form 0 over 0, which means the only way to figure out exactly what's going on in this limit Monsieur L'Hopital. Right. Take the derivative upstairs, take the derivative downstairs, and see if it tells you anything different. And in this example, it does after one application. So one application of L'Hopital's rule gives me in the numerator 1. And in the denominator, the derivative of the square root of 4x plus 1 is 1/2 times 4x plus 1 to the negative half. And then the chain rule is also going to give me an extra factor of 4 from the derivative of 4x plus 1. But now simplify this thing out. That 4x plus 1 to the negative half in the denominator becomes... Yeah, so downstairs I have the 2 coming from the 1/2 times the 4. But now the 4x plus 1 to the negative half, we can pull up to the numerator and make it 4x plus 1 to the positive half. Now what's happening to this limit as n tends to infinity? Yes, it does. Infinity in the numerator, 2 in the denominator. So this sequence, as n tends to infinity, also tends to infinity. The material we're doing is challenging enough. Don't make a simple problem into a difficult problem if you can avoid it. If I'm asking for the limit of a sequence, there's no series going on here. There's no addition. There's no tests. There's just, what's the limit as n tends to infinity? It's almost a Calc 1 kind of question. And L'Hopital's rule is the tool that we have to use in this example because our limit has the indeterminate form infinity over infinity. So let's talk about B. In B, you're being asked the question, which of these two sequences, and I have 1 over n squared on the one hand, and I have the cosine of 1 over n minus 1 on the other hand, I want to know which one of these sequences approaches 0 with higher order. So first of all, both of these sequences do in fact approach 0 as n tends to infinity. 1 over n squared, evidently, has the form 1 over infinity as n tends to infinity, so that definitely tends to 0. Meanwhile, the cosine of 1 over n minus 1, how do I know, by the way, that this approaches 0 as n tends to infinity? Yeah, as n tends to infinity, this looks like the cosine of 1 over infinity, quantity, minus 1. But 1 over infinity is one of our names for 0. But the cosine of 0 is 1. Yeah. So 1 minus 1, indeed, gives us 0. So both of these sequences, let's call them an and bn, as they were called in the problem, both of these sequences approach 0 as n tends to infinity. And so then the question is, which one of them gets there at the higher order. So what am I really asking you to do here? I'm asking you to compare the rates at which an and bn approach 0. And we have a comparison that allows us to do that. We call it the limit comparison. In other words, to figure out which one of these sequences approaches 0 with a higher order, I'm just going to divide one of them by the other and then determine the fate of that limit, of that quotient, as n tends to infinity. Except that now, our limit, again, has the indeterminate form 0 over 0. So how in the world am I going to figure out which one of these is approaching 0 with a higher order if the limit has an indeterminate form? L'Hopital. Again, L'Hopital is the referee. So what I really need to do is find this limit as n tends to infinity. And a number of you set this up appropriately. But then when you went to take the limit of this quotient, some weird things occasionally happen. So let's do this kind of one step at a time. If I apply L'Hopital's rule to the numerator and to the denominator, so taking the derivative of 1 over n squared and taking the derivative of the cosine of 1 over n minus 1, then first of all, what's the derivative of 1 over n squared? Negative 2n to the, it's actually n to the negative 3. Right, because we're decreasing the exponent, and the exponent began as negative 2. So if you like, we could rewrite 1 over n squared over here as n to the minus 2. And then its derivative is negative 2 times n to the minus 3. So there's the derivative of the numerator. And the derivative of the denominator, cosine of 1 over n. What's the derivative of cosine of 1 over n? Cosine becomes negative sine. But now what does a chain rule do here? It actually brings out more than a 1. It brings out the derivative of 1 over n. The antiderivative is ln. But the derivative of 1 over n, this is n to the negative 1. Negative 1 over n squared. Negative n to the negative 2 when we take the derivative of the 1 over n. So the negative from that piece and the negative in front of the sign, let's cancel those. And so here's what we have after an application of L'Hopital's rule. But before we do anything else to this, and this is where a few of you went off track a little bit, before we do any more analysis with calculus or L'Hopital or any of that stuff to this fraction, simplify it. Algebra before calculus, ABC. Let's take those powers of n that we have in the numerator and the denominator, and let's collect them all together. I have n to the second power downstairs. What does that become if I bring it upstairs? Well, it was n to the negative 2 down here. Right. So when I bring it upstairs, it becomes n to the positive 2. But n to the positive 2 and the n to the third in the denominator reduce, so that now what I've got upstairs is just negative 2 over n. So reducing everything with algebra as much as you can before doing any additional calculus is always a good plan, because then the calculus is simpler and you won't end up making conclusions that are too hasty. Because after all, before we can apply L'Hopital's rule one more time, which we're going to have to do here, we need to know that our limit is still indeterminate. And our limit is still indeterminate because the numerator, negative 2 over n, goes to 0 as n goes to infinity. And the denominator, sine of 1 over n, approaches the sine of 0, and the sine of 0 is 0. But now that we know this is 0 over 0, we can apply L'Hopital's rule one more time. And one more time should be all it takes. What's the derivative of negative 2 over n? Yeah, I'm going to get an n to the negative 2. But actually what comes down, the power that comes down is negative 1, so I just get 2 over n squared up here. So there's the derivative of negative 2 over n. What's the derivative of the sine of 1 over n? Sine becomes cosine. And then what happens? Yeah, again, the chain rule is going to spit out the derivative of 1 over n, which is, again, negative 1 over n squared. Negative 1 over n squared, so that's multiplying here. But what happens now that didn't happen before? Now when I bring that n squared from the denominator up into the numerator, it completely cancels out all the n's that I used to have upstairs. And so when the dust settles on this algebra, upstairs, all I have left is 2. And downstairs, I have cosine of 1 over n. Was it negative? Yes, you're right. Yep, there was a negative sign in my denominator that I almost forgot about. Thank you for saving it. There we go. Now, what does this do as n tends to infinity? The numerator, negative 2, approaches negative 2. It doesn't care what n is. The denominator, the cosine of 1 over n, approaches the cosine of 0. And so our limit is equal to negative 2. So that was the calculus part. That was the computation part. We began with the limit that was indeterminate, and we used L'Hopital's rule to resolve the indeterminacy and find out that the limit of this quotient is negative 2. That was the computation. Now, what's the interpretation? The whole point of us doing this computation is it was supposed to tell us which of our two sequences approach 0 with a higher order. So what does the result mean? What's important about this number? When we make a limit comparison, what are the 3 different possibilities? What are the 3 different cases that we can get for this limit? We could get 0, we could get infinity, or we could get neither. These are the 3 cases that are important in a limit comparison. 0, neither, or infinity. Because which of these 3 things that we get is going to tell us which between the numerator and the denominator has approached 0 more rapidly. Because we've gotten a quotient now in our answer in which neither the numerator nor the denominator is still going to 0. So who's winning the race to infinity if they both end up non-zero at the same time? Neither. In other words, in this race to infinity, both the numerator and the denominator have gotten there at the same order. So the possibility of a tie between numerator and denominator, in other words, they both get there at the same order, is always a possibility. And that happens in the limit comparison test when your limit of your quotient is neither 0 nor infinity, as it is in this case.